Welcome to the 2023 Earth Science Week webinar series based on our theme, Geoscience Innovating for Earth and People. Today's speakers will focus on the importance of locating, mapping, and sustainably sourcing critical minerals and materials. First up, we have Shah from the U.S. Geological Survey, who will discuss innovations that allow us to discover and map mineral resources in many different types of environments.
Hi, I'm Angie Shah with the U.S. Geological Survey, and I'm here to talk about airborne geophysics. We are in the midst of a very exciting time right now because the USGS is currently collecting an unprecedented amount of new public data across the country. Geophysical data provide unique ways of imaging geology beneath vegetation and also beneath the surface of the Earth. When surveys are conducted from an airplane, the resulting data sets can cover thousands of square miles. These data have many applications, but I'm going to focus on a specific one, which is critical mineral resources. So what are critical minerals? These are materials naturally occurring on the Earth that are considered essential for our economy and its functions, but for which there's a risk of supply chain disruption. These materials are needed for everything from cell phones to renewable energy to advanced defense systems. A classic example is the rare earth elements. For example, in cell phones, they're in the display and the speakers and the vibration units. They're also used in solar panels and to make magnets that are used to assist wind turbines. Another example is titanium. Because it's lightweight but strong, it's often used in aircraft and ships. At the same time, it's also rather inert, so it's a perfect material for medical devices such as artificial hips or artificial knees. Titanium is also used for white paint. Critical mineral resources have been very much in the news because of their importance to our economy and national security. Here are just a small number of stories grabbed off the internet. An awareness of the key role that they play led Congress to take action to help us gain better knowledge of our domestic resources. One component of this is the USGS Earth Mapping Resources Initiative, which started in 2019 and then in 2021 received a significant funding increase through the bipartisan infrastructure law. This funding is now supporting an unprecedented amount of data collection and geologic mapping across the United States. Analyses of these new data are in turn providing brand new insights into the geology of our country. All the data being collected are made available freely to the public. What kind of data are being collected? You might ask, in an era where a satellite can show detailed pictures of your home, what else is there to learn? Well, in parts of the country, these satellites are mainly showing us trees. We can't easily see the geology. We can't see the rocks. Also, often we want to know what lies underneath the surface. So how can we see deeper? To do this, we need specialized methods. An analogy is what's used in the medical fields, the way a sonogram, MRI, or X-ray allows one to see beneath skin. We use geophysical methods to see beneath the surface of the Earth. Geophysicists have a number of tools to image Earth beneath the surface. LiDAR, or light detection and ranging, is a way of obtaining high-resolution topography even beneath vegetation. Radiometric methods tell us about the geochemistry, specifically the potassium, uranium, and thorium within the upper 1 to 2 feet, and are also able to see beneath vegetation. There are other methods that use sound, electrical properties, or magnetic fields, but I'm going to be focusing on LiDAR and radiometric methods. What are radiometric methods? When potassium, uranium, or thorium are in rocks, they will decay to other elements, and as they do, they release a gamma ray that has a very specific spectrum. Our sensors can detect those rays and then use the shape of the spectrum to back out which element decayed. By counting the number of gamma rays with a certain shape, you can use that as a proxy for geochemical quantities. Radiometric surveys can occur from a number of different platforms. They can be flown from airplanes and covering a large area, or they can be carried while walking for very focused studies. When flying them from an airplane, magnetic and radiometric data are typically collected together because the survey designs are very, very similar. But regardless of the platform, for almost all surveys, measurements are often taken along a series of profiles going back and forth in a pattern somewhat like mowing the lawn. These profiles can then be combined to form a map. We do have broad radiometric coverage over much of the country. The map you see here shows thorium. This map was compiled from a series of surveys flown in the 1970s as part of a national uranium assessment. Here, yellow represents the higher thorium content and blue represents lower amounts. This sort of map can be very informative, but there are limits to the data if you try to use them for a more local study. First, the data were collected in the 1970s before there was access to GPS technology. Also, the sensors and processing approaches are now outdated. But most importantly, to cover the entire country, the space between each flight line was very wide, typically 3 to 6 miles between every line. For a local survey, one wants something more like a couple hundred feet, maybe up to 1,000 feet. In fact, before Earth MRI, there were very few airborne radiometric surveys flown at high enough resolution for local studies. These are shown in orange and red on the map. The gray areas show the broader surveys with very wide line spacing. But after 4 years of Earth MRI, the landscape has completely changed. Each one of these purple polygons represents a high-resolution airborne magnetic and radiometric survey. The areas were chosen because of their prospectivity for critical mineral resources. So, how can we use all these new data to learn about critical mineral resources? For our example, we're going to go to the beach. You might ask, what does the beach have to do with critical minerals? Here's video taken on a windy day at the beach on a barrier island in South Carolina. You'll see that the wind is blowing light-colored sands and leaving the darker sands behind. This is because those darker sands are denser and heavier than the light-colored sands, which makes it harder for the wind to pick them up and carry them. The working of the sands by the wind has an effect of sorting the sands and separating the light-colored, lightweight sands from the darker, heavier sands. Waves can also have a similar sorting effect. Here you'll see a wave come in, bringing in both light and heavy sands, but then as the wave recedes, it takes away the light sands with it, leaving the darker, heavier sands behind. This winnowing also works to sort and concentrate those sands. Note there's a very different environment behind the beach in the tidal bays where the water is protected by the barrier island. This is a much quieter environment which allows vegetation to grow. Why are we so interested in sand? It turns out that in the southeastern U.S., these dark, heavy sands contain critical mineral resources. That includes ilmenite and rutile, which are high in titanium, zircons containing zirconium, and monazite and xenotime, which contain rare earth elements. It turns out that nearly 70% of our global supply of titanium and 100% of our global supply of zirconium all come from heavy mineral sands. Sands also used to be the primary source of rare earth elements through the 1950s until production moved to other deposit types, specifically carbonatites and clays. There is renewed interest in obtaining rare earth elements from mineral sands, and several groups are working on improving that technology. One of the challenges is that the monazite contains thorium, which requires special handling. At the same time, because the monazite contains thorium, we can likely image it along with co-minerals containing titanium and zirconium using airborne radiometric methods. A beach can tell us a lot about how heavy mineral sand deposits form, but it's not a good site for extracting minerals because of other important land uses. It's much easier to go inland to ancient beaches that are thousands to millions of years old, lying just beneath the soil. This is a photo of a mining operation in Virginia taken in 2012. At that time, the topsoil had been removed and placed aside, exposing the sand underneath. Processing the sand is all done by physical means through spirals that further sort by density, such as to the left, or by other separation methods, such as magnetic or electrical fields. The waste product is light-colored quartz sand, which is then placed back in the ground. After that, the topsoil is put back in place and the area remediated. How can we use airborne geophysics to learn more about heavy mineral sands? We're going to go to South Carolina, where a pair of Earth MRI magnetic and radiometric surveys were flown. This pair of surveys represents multidisciplinary interests. Along with heavy mineral sands, for which we'll use the radiometric data, this region also has a significant earthquake hazard risk. In 1886, it was the site of a magnitude 7 earthquake which nearly destroyed the city of Charleston. Low-level seismicity continues today, and the causative fault of the 1886 earthquake remains unknown. One goal of the surveys was then to use the magnetic data to image deep buried faults that could potentially rupture. But that's a story for another time. The images to the right show the survey airplane. You can see the inside of the airplane. The passenger seats were removed to make room for computer equipment and the radiometric sensors. Those are the big black boxes. The bottom shows the airplane from the outside, and it's quite unique. There's a boom sticking out the back, and that boom houses the magnetic sensor. The reason the magnetic sensor is placed there is to keep it away from the magnetic field of the airplane. It produces much cleaner data. The area surveyed by both was in total about 134 kilometers by 212 kilometers, or about 80 miles by 130 miles. This image shows those data that were collected in the 1970s with very wide line spacing. Again, it's the thorium channel. And for comparison, to the right, we have the brand new data. You can see there's quite a lot more detail. Note, north isn't up in these maps. Up is actually northwest, and down is southeast. Down is where the Atlantic Ocean is. The survey covers a long swath of Atlantic coastal plain sediments. Near the top in the northwest is the crystalline rock of the Piedmont province that's the source of the sediments. Just below that, in the bright orange-yellow area that includes Columbia, are the oldest sediments that were deposited shortly after the Atlantic Ocean first opened. Near the bottom of the map to the southeast is what's called the lower coastal plain, with younger sediments of roughly the last 2 million years or so. This area is very geologically similar to actively mined deposits in Georgia and Florida, so that's the area we're going to focus on right now. The results I'm going to present were published in the November 2021 issue of GSA Today. Let's look at this data set more closely. To provide context, this image shows a drape of the thorium anomaly over a shaded relief elevation map derived from LiDAR data. From the LiDAR, it's much easier to see the specific landforms. First, notice the light blue areas at the bottom of the map. That's the Atlantic Ocean, and also in the middle of the map, which are Lake Moultrie and Lake Marion. These light blue areas all represent water. The gamma rays can't escape the fluid medium, so the thorium values are very low. Next, to the right of Lake Moultrie, and where Lake Marion has been dammed, you'll see a bright yellow area. This is the floodplain of the Santee River. We can see the signature of the sediments from the floodplain because the lake has been dammed and the floodplain was relatively dry. Then just to the right of the Santee River floodplain, you'll see another bright yellow area, and those are all windblown sands, also referred to as aeolian sands. Now look back to the main part of the map, and you'll see a number of ridges just going across the map. These are all ancient shorelines or ancient beaches from thousands of years ago. But then in between the shorelines, there's this popcorn texture areas, and those are tidal bays or the back barrier. There the sediments are a lot finer, much more like clay rather than sands. But what do the colors represent? The idea is that the higher thorium represents monazite in heavy mineral concentrations, but how can we be sure? Well, it turns out my USGS colleague Rob Weems, who's now retired, has spent many years of his career in the region collecting samples to map out those areas which have heavy minerals. Over decades, he collected over 1,000 auger samples. The red dots on this map are those samples that showed the highest heavy mineral concentrations. The purple dots had very little or no heavy minerals at all. And if we zoom in a little bit, you'll see there's actually a pretty good correlation between the samples and the airborne data. And this is especially because the data represent an average over several hundred feet. There's a data footprint. But with heavy minerals, there can be a lot of variation at the most local scales. So this is a very good correlation. What the samples don't show, however, is the context of the heavy minerals. The advantage of the geophysical data is that we have continuous coverage. We can connect the dots. And we can learn even more by using existing geologic maps. To the right is a map showing areas with sands versus clays that was derived from a composite of several dozen geologic maps. Here, the tan colors represent sands, like the paleo shorelines. The brick represent clays, essentially those back barrier tidal areas. The blue shows river floodplains, and the dark blue and red shows areas that have been modified by people, such as landfill. We can then use GIS to look at the data only for sands or only for clays. So here, this image shows everything except sands has been shaded out. And you'll see here that the paleo shorelines, and they're mostly blue, but with very localized bright yellow areas. This suggests that there are these small areas where heavy minerals are concentrated, but elsewhere on the paleo shorelines, there's not many at all. Now note, small is relative. Some of these areas are several miles long. In contrast, if we do the same thing by shading out everything except the clays, highlighting those back barrier tidal bays, we see that the colors aren't as bright. They're more red than yellow, and the thorium anomalies are much more evenly distributed. They aren't focused in a few locales. This suggests that there are heavy minerals in these back barrier areas, but they're more dispersed. Well, note though, without strong concentrations, an environment like this is less likely to be economic. If we zoom in on the drape over LiDAR, you can start to see certain patterns. See the areas marked by the stars. You'll see that bright yellow anomalies, which should have the greatest heavy mineral concentrations, occur where there are angles, in other words, where two paleo shorelines appear to cross each other. These are areas that have been shorelines more than once, but with slightly different orientations. This means that these specific areas have experienced multiple episodes of reworking by waves, tides, and currents. All of that reworking has concentrated the heavy minerals into a few locales. Ultimately, this is just one example of how airborne geophysics can tell us about geologic processes associated with mineral deposit formation. There's also more to the story that can be learned from the other channels, especially potassium. But the goal today is to give a flavor of how interpreting these new data might be done. Plus, I'm running out of time. For more about this data set, please see the GSA Today paper. And before you go, I also want to highlight that this study represented only one small part of the country. There are many more new data sets out there with stories to be told. If you'd like to learn more about Earth MRI, please visit our website listed here. And stay tuned as we continue to learn more about U.S. geology and our natural resources.
Thank you, Angie, for showing us how the USGS is collecting data on critical mineral resources. Next, we will hear from Cynthia Howell and Dr. Rod Eggert. They will discuss the role of Critical Materials Institute in developing innovations in the use of critical materials, as well as their education and outreach programs they provide for students, educators, and the general public.
Hello. I'd like to welcome you today to our presentation on Critical Materials Institute, which is for the Earth Science Week celebration. And I'd like to introduce one of our two speakers today on creatively leveraging collaborations and community assets and what is the Critical Materials Institute. And that is Dr. Rod Eggert. And today he will talk to you about CMI. He is the Deputy Director for the Critical Materials Institute. He is a geochemist turned economist and is a professor and Coulter Chair for Mineral Economics. And I don't want to take any more time from your presentation, so if you would take it away, Rod.
Thank you very much, Cynthia. The primary purpose of this presentation is to discuss the education and workforce development activities of the Critical Materials Institute. Let me set the stage for this discussion by answering two questions or asking two questions. First, what is a critical material? And second, what is the Critical Materials Institute? Next slide, please. So what is a critical material? A critical material is a material that has two characteristics. First, it is essential in a modern engineered technology or system. And second, its availability is at risk, either in the short term due to geographically concentrated supplies or a limited number of production facilities, or over the longer term because of concerns about longer term availability. So, for example, we're talking about things like certain rare earth elements in state-of-the-art magnets in the most efficient electric motors. We're talking about lithium in lithium-based batteries. We're talking about gallium in certain electronic materials. We're talking about copper in essentially all aspects of electrification. So that's what is a critical material. What's the Critical Materials Institute? Next slide, please. The Critical Materials Institute, or CMI for short, is a research consortium funded by the U.S. Department of Energy. We were founded in 2013. We are led by the Ames National Laboratory, one of the Department of Energy national labs. We are a consortium, so we have working together researchers from the national labs, from universities and companies. Our mission is to accelerate innovation that will help secure supply chains for critical materials for energy applications. We conduct research at the early stage, and by that we mean at a laboratory scale in several focus areas. One focus area is enhancing the processing of material once it's mined. A second focus area emphasizes enhancing manufacturing efficiency, recycling and reuse. And a third focuses on developing new materials that use less of or eliminate the use of the materials deemed at risk. The Critical Materials Institute has several products, and we've had a number of achievements over our 10-year life. Next slide, please. Simply in terms of the numbers, approaching 200 invention disclosures, 44 awarded patents, 20 technologies licensed or optioned by companies, approaching 600 publications, and more than $80 million of follow-on funding to help test and scale up these technologies at scales larger than the laboratory scale. We've also won, our innovations have won a number of R&D 100 awards, and those are identified. Several of these are identified and explained here. But that's enough about what is the Critical Materials Institute. Let's turn our attention now to the education and workforce development activities of CMI. And so back to you, Cynthia.
Thank you so much, Rod. And thanks for that great intro for CMI as well. Now we're going to talk about how do we get research concepts to the public and into the classroom. And so today I'm going to walk you through our creative collaborations and community developed outreach assets and tools. And I'm hoping that you might see some value on how this might fit into your workplace and or classroom. And as I take you on this journey, I hope that you'll begin to see why this outreach is so engaging for students. And one of the most important reasons is it's in all of the things that they use and that are near and dear to them today. Their phones, cell phones, their computers, also electric vehicles. They're interested in the future of green technologies, wind turbines, solar panels, so on and so forth. So it just gives them an idea of what critical materials are and what's in their devices. And maybe that's why it's so expensive. So is that material hard to mine? Is it rare and only found in other countries? Or is it high cost? So there are lots of things that they get to think about when they enter the world of critical materials. So we do work on supporting the future materials workforce through our outreach. And we are hoping that through some of the products that we developed that people get to imagine about new things, new innovations, as well as what's in their current technologies that they're using today. We're trying to build a pipeline of K through STEM. And while we take STEM into the classrooms, we hope that these young people start getting a little bit of a STEM identity and thinking, maybe I'd like to do something like this in the future. I'd like to be engaged in some of this research. We collaborate with universities, national laboratories, industries, within our hub and without our hub. You'll see as we move on, and then connections are made by tracking our workforce and career movement. You're going to see all of this as I move you through some of our work. The picture to the top is a group of young children engaged in our interactive piece of the museum exhibit. And definitely not in school yet, so preschoolers, but isn't it fun to see them already curious? Down below, we have a group of teachers in a learning setting, and that's part of our role as well. We try to not only develop materials that are important to educators and that they will use in their classroom or in their workplace. So the exhibit is one of our greatest assets. And as we were talking before about, finding what's local, what are your local and national assets and partnership possibilities. This museum happens to be on the Colorado School of Mines campus. It is internationally noted. It brings in about 30,000 visitors annually. And it links in our exhibit, we have linked advanced technology to materials needed and the sources of the materials. So if you look at the picture to the top, you see a group of high school students. There was about 30 in the group, one of our tours, and they are engaged in the CMI exhibit, and it looks like they're in the mining processing piece. And if you see the one to the middle, that is, I bring it, have a teacher working with me. We have our teacher, a graduate student, undergraduate student, looking at the exhibit pieces and determining where we can make upgrades and changes to keep the exhibit fresh so people can come back year after year and still be engaged in this particular exhibit. And down below, you'll see a picture of some of the specimens that we have in there. They are high quality museum specimens. So critical materials don't look like that when they first come out of the earth. These are brushed and polished and put up for museum view. But it is wonderful to be able to put a exhibit piece together like this. We focus on critical rare earths and metals, responsible mining and processing, use of materials and energy and advanced technology. We have some solar panels outside of the museum feeding energy into one of our exhibit pieces. And again, we feature our CMI research, which is the most important piece of this exhibit. We also have a educator researcher toolkit, and we developed this toolkit for people to take into a workplace setting and or a classroom. And so they have little demonstrations on raw critical materials, how it's vital to energy and advanced technologies. It's accessible, it's versatile, it has lesson plans in it. And if you look at the lesson plans, we also feature those same lessons on the Materials Education Mat.edu site, which is hundreds and hundreds of material science education pieces in that portfolio, but we're glad to have our piece with critical materials. Some of the highlights, we've got neodymium magnet comparison, strength and induced force demos, recycling critical materials to meet demands. And again, this is a physical kit. It can be found at the aimslab.gov website, described, and pictures of it as well. Colorado teachers can check it out of the museum. And I've also sent some out nationally. So if we have a request and it's one that would really use this kit over and over again, there's a possibility we would do that for you if you're thinking about that. We also conduct outreach events, and one of our outreach events happens to be National Engineers Week, where we join with Lockheed Martin, a couple of other research facilities, and we put on a day where we invite seniors in the area to our campus. We, over the years, have had about 700 Colorado students onto our campus for this special event with 89 national during COVID. We offer tours of research and laboratory spaces. That's so rare for students to be able to see and do. And we also take them to the CMI exhibit. One special component is during lunchtime, we do a career mentoring session with all of the students. And we have a Lockheed Martin and Mines combination sitting at the table, and we talk about going to college as well as careers available and in STEM. So a really exciting day. We also partner with and work with Rocky Mountain Math Engineering Science Achievement, and CMI along with Nexus are two of the research centers that really help support this organization. And it is an organization that takes STEM into classrooms, and our graduate students actually go out into those classrooms and help students build engineering designed prototypes that they will bring together to show at the Mesa Jamboree, and some of them will compete in the engineering design competition. And the winner of the engineering design competition gets to go to nationals. This past year it was in Albuquerque, and Colorado won. Woohoo! But important thing about the Jamboree is we bring together scientists as judges. We bring them from all kinds of areas. They're from the National Renewable Energy Lab, Lockheed Martin, professors on campus, energy resources. We just have them from all over the state of Colorado coming in to judge, and that is really exciting for the students as well to have those professionals there. So the top picture at the beginning was my introduction of Engineers Week to the students that would be attending. The picture to the far left and rear and end is all the students that participated in the Rocky Mountain Mesa Jamboree on our Colorado School of Mines campus. And to the right, that's a picture of students going into a laboratory and learning about what they do in that laboratory by one of our graduate students. So again, you look at the resources that you have locally, and you take those and you try to build interesting products and events. So how do teachers and researchers use our education products? Well, a lot of ways. We can partner in a lot of things, but these toolkits lessons, they reach a variety of students and the museum and faculty. So they're really a K through grade opportunity, and it helps students learn about materials that they engage with daily, as well as what are some of those high-tech things, possibilities in the future. So the museum exhibit, it is an in-person experience. We've had researchers that come into our winter meeting, and they come to see it every year because they get to see their research. And had they not had that trip, they wouldn't be here. So it's local, but you can also visit a little bit of it remotely on our website. We talk about the museum exhibit, we highlight it, we show some pictures, and we talk about how one goes about creating such an exhibit. The toolkits, we engage students interactively through demos, activities, discussions. They are available for Colorado teachers to check out. Again, I mentioned if somebody's interested nationally and there's a need and it's something that they would use often, I will either offer the materials that go into the kit, information about it, or potentially a physical one sent your direction. We've had this summer, we had a professor at Arizona State University who actually is one of our CMI members, use it to teach an engineering summer camp. And so she used it every day and used every one of the materials, every one of the lessons, and was grateful to have it in her hands. Again, she's one of our CMI members, but that did get shipped to Arizona. We also shipped one out to Idaho for one of our lab members. He wanted to use this to share with a advisory council. And he said in the end that he really felt that the advisory council gained greater understanding about the properties of rare earths and the importance of the critical materials research. So again, it can be used multiple ways. Here's our website, CMI Workforce Development at Ames Laboratory, where you can see all of these assets and actually engage in the lessons and pull those down for your use. We're hoping that everybody gets to engage in curriculum-based, most recent and relevant critical materials research topic areas. That's what these materials, museum exhibit, lessons, toolkits are all about. We're hoping to connect educators and students to relevant areas of research, connect all of us as we work through presenting critical materials in our outreach settings. And also, we're hoping to really inspire the future workforce. When you see them look at the exhibit and see how this connects to something that they have in their hand, their phone, and really what goes into all of that, they have a greater appreciation and of the value of these materials. For our early career, undergraduate, graduate student, and early career, we have a couple of things that we offer. Early careers, some individuals are selected to become part of a leadership academy, which gives them a year of leadership and management training. They also get to design something that they think is important for them, where they might have a gap in learning or where they just want to know more about. This particular group designed a short course called Rare Earth Elements, Mind, Magnet, and Beyond. And it was a success. If you look at the picture at the top, all of the people spiraling down the staircase, those were the attendees of the workshop. And to put it on for the first time, again, it was a huge success by all of the attendees. And their comments were such that it was a great experience. So at the bottom, the picture, you'll see the flanked by the deputy director on the left and the director on the right, you'll see the Leadership Academy, and they're the ones that designed this short course that will be a part of our workforce development portfolio, and I'm sure it will be presented again due to its huge success. We also do a winter meeting on our campus, and it focuses on workforce, and it allows undergraduate, graduate students, or more graduate and postdoc and early career people to present their professional work. There were 20 oral presentations and 6 posters in this last winter meeting. The top photo shows you all of the presenters. The bottom photo shows you all of the people that came from throughout the nation, part of the CMI membership and affiliates, to support this meeting and provide networking opportunities for our early career professionals. And connecting sustain by tracking workforce. So we stay in connection with our students and our early career professionals by tracking them and seeing where they're going. And it's exciting to see that many of them have left the CMI for other positions in government, national laboratories, universities, industry, early startups, nonprofits. And these are students to the right that, Kayla doing an extern at Idaho National Lab, Rakesh, Advanced Materials Laboratory, Philip, Energy, Fuels, Resources, and so on. And we have we could have plastered several slides with success stories of young people moving on to their next career, and as a result of having this experience. So I want to thank you today for giving us an opportunity to talk to you about the Critical Materials Institute and what we do, and share with you some of the resources that we've developed for outreach and workforce development as well. We hope that you find that some of them might be of great value to you in your workspace and or your classroom. And if you notice at the end of all of our supporters and all of our membership in the center here, I have my email, chowell@minds.edu, and I'd love to hear from you if you have any other ideas of partnering, of any ideas of additional outreach, and something that we might have that would really enhance what you do. So again, thank you so much for your attention and this opportunity to present to you during Earth Science Week.
Thank you, Cynthia and Dr. Eggert, for explaining the work of the Critical Materials Institute. We appreciate the time all our speakers took to join us today to discuss the future of Earth's critical materials. Thank you so much for your attention today to today's webinar and the presentations on critical materials and their importance in the future economy. I'm Lindsay Amosa, and I am an education specialist with AGI, and here to continue the conversation and get some questions answered from the speakers today. So I'm going to invite our speakers to turn on their cameras. Welcome. Thank you so much for being with us to be able to answer these questions. I see we have quite a few. I'm going to encourage those who have hands raised to put their questions in the chat. So it's a little bit easier for us to manage. But one thing I wanted to start off with, since this year's Earth Science Week theme is Geoscience, Innovating for Earth and People, I wanted to hear from each one of you on a little bit about why innovations are needed in the area of critical materials and minerals. So Angie, if you want to get us started. I believe you're muted. Oh, happens in every good meeting, right?
I know. And you think we would have learned by now after all this time. Thanks for asking that. Yeah, innovations are so important. There's I can see that on the research end, sometimes there's been a thought that, a lot of, well, where can we find critical minerals? And there's a feeling that maybe we're starting to hit a knowledge ceiling that we don't know. But what happens is that the more and more we use other methods and use sort of innovative methods, and I gave the example of airborne geophysics. That's one of them. But the more we get more data and the more we learn about the geology of our country and actually in the world, then the more we can learn about critical mineral systems, the more we can learn about where they're located, the more we can learn about also how to, if we need to extract them and if it's appropriate to extract them, how can we do this safely, and how can we do this safely for the surrounding communities? So there's and so we learn more about Earth as a system by having these innovative data technologies and thinking about the whole system, about where are the minerals, which ones are useful, and how can they be extracted safely, and how can areas be remediated safely. So yeah, it's great. I mean, we're getting a lot of data now. And another key thing about the innovation is that a lot of the data that we get to learn about the Earth has applications to a lot of other fields. I can say, for example, earthquake hazards is a big one. For some methods, looking at radon mitigation. In some cases, understanding water resources, understanding other types of geohazards, and so on. So,
Fantastic. Thank you so much. And Cynthia, as you talk, we have a lovely slide to share because I know you have some innovations of your own that you would like to share with the audience today.
Yes. And, it is good to be here today because, again, the mission for Minds, or for the Critical Materials Innovation Hub, notice we have a little bit of a name change here on our next 5 years. CMI has been in existence for 10 years and has been conducting research throughout all of those years. And again, as Dr. Eggert had mentioned, major innovations, major patents, so on and so forth. So it is among our mission to accelerate innovations. That's what we do every day. And for myself, as doing the workforce and training and education outreach, I really liked the comment that was mentioned that the more we learn and know about materials and systems and so on and so forth, it really helps drive our economy and our world forward. And as a outreach person, the exciting part about that is high tech is really everything that we have, from medicine to electric vehicles, transportation, energy, so on and so forth. It goes across all sectors. Students are engaged in it every day. So young people are engaged in that. They love new high-tech tools. And this really is the way to encourage them to be engaged. Once they learn about what's in those high-tech tools and they think about, where would I like to be engaged in working with high-tech development of tools? Maybe that's in the biomedical field. Maybe it's in energy, so on and so forth. So it really makes the job that I do and trying to reach young minds and really K through gray about the work that we're doing, it's trying to inspire them and engage them in this type of work and thinking. Along with our innovation hub, a couple of things that we have going on for us in the near future here. We'll be starting up our monthly professional development webinar series, and that's always advertised on our website at aimslab.gov. Also, we are quickly approaching National Engineers Week, and we reach across our 300 researchers across the nation to try to pull together many events that are going on in the area. And I shared with you one that we do locally on our Minds campus that is a huge success, but that happens in many other areas across our nation as well during that time. This is fun to be engaged here in Earth Science Week. It's just fun to really be able to reach out further by partnering with such people, many different industry members, so on and so forth, and today with AGI. September 23rd, we launched our Rocky Mountain Math Engineering Science Achievement Year, and we have about 10 schools with 600 students engaged, and it really is our graduate students who we train and have training sessions for monthly that go out into the schools and really engage students not only in engineering methodologies, but also have a lot of discussions about career and school. And again, we want all of these students, most of them underserved populations, we want them to have college as their goal. So those are the things going on in our area, but research-wise, the innovation continues. And as Rod had explained before, we have a new 5 years to continue the work that we've been doing the past 10.
That's fantastic. I know there's a lot of geoscience professionals here today, and really encouraging them to get into the classroom and engage with students and talk about, kind of what's coming up in the geosciences is really just as important as the concepts themselves. So absolutely love the work you're doing. Thank you.
Thank you.
So I see that there's some questions in the chat. So thank you, Angie, for posting a few links to address some of those already. But I think the first one that was not addressed might be for Cynthia. Yeah, Cynthia. Someone asked that you put some links in the chat as well for online outreach materials that can be accessed digitally, and that would be fantastic.
Okay.
And then I believe for Angie, there was a question about, sorry, I lost it for a second there. So one of the links that you shared was on information and listing critical materials and the projected demand for those. Did you want to speak a little bit more about this topic for, what do we really know about the future demand of these, or do we?
Yeah, that's a great question. So a lot of that work is done at the USGS through our National Minerals Information Center. I'll be honest, I don't work with that group, but I talk with them, and my gosh, they are so knowledgeable. At the same time, they do their best to document what is happening today. There's a lot of research going on in terms of trying to predict what will happen in the future. And I can say that, this isn't something I specialize in, but I've seen the various studies and they're all over the map. The one thing they have in common, though, is that everybody expects critical minerals usage to increase, especially on a global level. We have a certain, say here in the US, many of us have computers on our desks or we have cell phones, but there's a lot of parts of the world where that's not the case. And as populations want to obtain more of these tools and more of these materials, that need is going to increase. So, there's a big question. I think I saw someone talk about supply chain, and it's a big question as to whether or not we'll meet the supply chain. And, I can say I've seen other discussions that, right now for the USGS, copper is not on the critical minerals list, but I've seen some scientists argue that perhaps it should be because, say, for an electric car, along with all these special materials you need for batteries and so on, you also need copper for the wiring of a car. So, it's just a really active area of research. So it's really hard to generalize in that regard, but I hope that sort of answers the question.
Yeah, I mean, it seems like there's an ongoing conversation in the chat really about that supply chain, which I see you had noticed, but maybe one of you or both of you could speak a little bit on any work that you know of for reclaiming materials or recycling of materials that's going on in order to contribute to the not so much need for extracting more materials.
Yeah, actually, I can definitely speak about that. At the USGS and also Department of Energy and a number of other agencies, there's a lot of interest in trying to obtain critical minerals from mining waste. And this mining waste can be metallic mining, or it could be industrial. So for example, if you remove some phosphates, there might be critical minerals in what was in the overburden. There's a lot of interest in getting this from coal waste, especially in the Appalachians, where there's been a lot of mining and there's a huge number of waste piles. It's an ongoing area of research. And one of the advantages of this is that in the process of trying to obtain minerals, you can also work towards remediating a lot of these mine waste areas. So it's a win-win on multiple fronts. The challenge behind this, and it's something that everyone's working on doing and wants to see happen. The challenge is that it looks at this point that the amounts you can get from mine waste, it's very complicated because the materials aren't always in the most easily used form. There's a lot of diversity to host minerals, so they're harder to extract. Other issues is that they tend to be smaller amounts. So there's a lot of question as to whether or not it's economic. So, is this something that perhaps if you want to remediate an area, you can at least get some economic benefit during that remediation? Is there enough to meet our demands, the necessities on even a national scale? It looks like everything I've seen seems to suggest not at this point, even though we would love for that to be the case. And I think Cynthia has comments. Yeah.
Oh, I'm sorry. Yeah, I was going to say I ditto
Yeah.
Angie all the way through all of the comments. And again, this is where CMI comes in at the research level. We are doing research on extracting materials from mining waste. We're also trying to find ways to make mining more efficient so that it's a closed cycle and circle, that what comes out of the earth, including water, goes back in, and it's just one nice cycle all the way through. So we're doing a lot of research on mining waste, as well as we talked about the tailings off the manufacturing floors. So if you're working with the magnets and the tailings and scraps that come onto the manufacturing floor, again, gathering those and finding efficient ways to extract the precious metals and minerals from such manufacturing items, as well as finding less toxic ways to extract minerals and materials from ore. And that's kind of, again, from the very beginning, that extraction process. Angie mentioned economics. It can be very expensive. It can be toxic, with the chemicals that are being used. And so we're looking at many other ways of extraction and have had some good success. And then also for things, we're also looking for substitutes. And for instance, a red phosphor or phosphor that has been being used in all of our computer panels and our TVs, any screen, the red phosphor actually has been a substitute has been created for that out of Oak Ridge National Lab, and so it's more cost effective. Again, a less chemically toxic method that they're using. So we are also, again, looking for substitutes in many different ways to replace these materials. And sadly, just as Angie had stated, we do not have all of the minerals, materials that we need to keep even our country going, much less the rest of the world. We're finding new deposits daily. Again, when we look at innovations, something that we just put into our exhibit is what's the future of mining? And we have two things actually being done now and investigated currently, and that's seabed mining. And when Angie talked about the rich soils, the dark soils that have so many of those materials, well, now they're looking and finding even richer soils under the ocean. So those are things that potentially may happen in the future. The next one is space mining. And even on our campus at Colorado School of Mines in our Space Resources Center, we're already looking at mining possibilities in space. So bringing back materials and finding that they're rich in one of the material areas. And what does that take? Again, economically, are these things feasible currently? No, but in the future, in a couple of decades, might we see people going to school for mining in seabed or space? So it's, again, all the innovations here.
Absolutely. Well, great. Thank you so much. It looks like we are now out of time. I was just excited to hear what you said and wasn't even paying attention to that. But now that we're out of time, if there are additional questions that did not get addressed, you can email us at webinars@americangeosciences.org and we can forward your questions on to the speakers. Also, we have been recording today and we'll be posting that recording within the next week on our webinar webpage. And we have a final webinar within this series. Tomorrow afternoon, we will hear from Vitor Croia, who will be speaking about how innovations in robotics are improving mining practices in Europe, so very much related to today's talk. Thank you so much for attending today's webinar, and thank you again to our speakers and all of your insight from the questions that came from the audience. Thank you so much.
Thank you.
Thank you.